second partial test or d-test to determine whether or not a critical point is a local maximum, a local minimum, or a saddle point. We can use the following test known as the second partial test or the d-test. Suppose that the function z equals f of xy and the first partial derivatives and the second partial derivatives are all defined in an open region R, and that the order pair AB is a critical point in the region R such that the partial f with respect to x equals 0 and the partial f with respect to y equals 0 at AB. Define the quantity D as D equals the second partial derivative of the f with respect to x multiplied by the second partial derivative with respect to y minus the second partial derivative with respect to x and with respect to y power 2 at the point AB. In case 1, if d is greater than 0 and the second derivative with respect to x is greater than 0, then the function at AB is a local minimum. Case 2, if d is greater than 0 and the second partial derivative with respect to x is strictly less than 0, then the function at AB is a local maximum. Case 3, if d is less than 0, then the coordinate a, b, and the function at AB is a saddle point. Case 4, if d equals 0, then the test gives no information. Let's take a look at the example. In this example, we are going to find all local maxima, local minima, and saddle points for the given function. In part A, f of xy equals negative 7x squared minus 5y squared plus 28x minus 40y minus 4. We're going to use the d-test. Where we're going to find the critical point first. Solving for x and y using the partial derivative of the f with respect to x equals 0 and the partial of the f with respect to y equals 0. And after that, we're gonna find the quantity d from the second partial derivative with respect to x times the second partial derivative with respect to y minus the second partial derivative with respect to x with respect to y quantity squared at the point AB that we're gonna find from the first step. All right, so for the partial derivative with respect to x is negative 14x plus 28, let it be 0. Partial derivative with respect to y is negative 10y minus 40 equals 0. For the first equation is only the function equation involving x. So we solve for x equals negative 28 over negative 14 or 2. The second equation, just the equation involving y. That's nice. So we have y equals 40 divided by negative 10 or negative 4. Therefore, the critical point located at the point AB equals 2, negative 4. Then we're going to use it for the second part of the process to find the quantity D. The quantity, we're going to need the second partial derivative with respect to x. From the first partial derivative, we find another partial derivative with respect to x to get negative 14. And the second partial derivative with respect to y, we got negative 10. With the second partial derivative with respect to x with respect to y, we're going to get 0 for this case. So the quantity D equals f of x, which is negative 14, times f of yy, which is negative 10, and minus f xy power 2. And after that, we're going to replace with the quantity AB, which is 2 negative 4. In this case, the D is positive value 140, which is positive number. So when we have d greater than 0, it's going to be either case 1 or case 2. So we're going to check the value of the f(x)(x) or the second order partial derivative with respect to x. In this problem, second order partial derivative with respect to x is negative 14, which is less than 0. If it is less than 0, similar way thinking of the function of one variable, the function concave um, concave down. So in this case, the critical point gonna give you the local maximum. So we can say that the local maximum is located at 2, -4. And when we are looking for the value, we're gonna substitute into the function. So the function at 2, -4, which is -7, 2 squared minus 5, -4 squared plus 28 times 2 minus 40 times -4 and minus 4 equals 104. So we can say that the local maximum point is 2, -4, 104